Training a deep model can feel like you are trying to steer something powerful through fog, because small choices in the training setup can decide whether the model learns a useful pattern or spins into instability. The good news is that you do not need to memorize a pile of formulas to train safely at a conceptual level, but you do need to understand why training sometimes fails and what the common safety rails actually do. When beginners first meet optimizers, learning rates, dropout, and batch normalization, it is tempting to treat them as magic switches that you flip until the score improves. That approach often leads to models that look good briefly, then collapse when conditions change or when the data shifts even slightly. A safer mindset is to treat training as a controlled process of making many small, reliable improvements while preventing the model from becoming overly confident or overly specialized. If you can explain what each mechanism is trying to protect you from, you can make smarter choices and diagnose problems more calmly. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A deep model learns by repeatedly adjusting its parameters to reduce a loss, and those adjustments come from gradients that point toward lower loss. The optimizer is the method that decides how to turn those gradients into actual parameter updates, and it matters because not all gradients are equally trustworthy. Some gradients are noisy because they were estimated from limited data at a particular step, and some gradients point in directions that look good locally but lead to poor generalization. The optimizer also determines how quickly the model moves through parameter space, how it handles sharp versus flat regions of the loss landscape, and how it reacts when the gradient direction keeps changing. Beginners often imagine training as rolling downhill to a single perfect point, but real training is more like navigating a landscape with valleys, ridges, and plateaus, where the same loss value can hide very different model behaviors. A safe training approach assumes you will encounter noise, instability, and misleading signals, and it uses optimizers and learning rate control to keep progress steady rather than dramatic. One foundational optimizer concept is stochastic gradient descent, (SGD), which updates parameters by using gradients computed from small batches of data rather than the entire dataset. The word stochastic reflects the randomness introduced by sampling batches, which means each update is an imperfect estimate of the true direction that would reduce loss on the full dataset. That imperfection sounds like a flaw, but it is also a feature because noise can help the model escape narrow, brittle solutions and find flatter regions that generalize better. SGD is conceptually simple and often surprisingly strong, especially when paired with learning rate schedules and momentum, but it can require careful tuning because it is sensitive to step size. A common beginner misunderstanding is to think SGD is outdated compared to more modern optimizers, when in fact it remains a reliable baseline and is widely used because its behavior is well understood. Safety here means respecting that noisy updates can help, but only if the learning rate is controlled so noise does not become chaos. Modern training often uses adaptive optimizers that adjust step sizes automatically for each parameter based on the history of gradients. Adaptive moment estimation, ADAM, is a well-known example, and the intuition is that it tracks moving averages of gradients and gradient magnitudes, so it can move quickly in dimensions with consistently small gradients and cautiously in dimensions with large or volatile gradients. This can make early training faster and less sensitive to the raw scale of features, which is why beginners often find ADAM easier to get working. The trade-off is that adaptive optimizers can sometimes converge to solutions that do not generalize as well as those found by carefully tuned SGD, especially in some settings where the model can exploit shortcuts. That does not mean ADAM is unsafe, but it does mean you should not treat fast convergence as proof of a better model. Safe training means you judge success by performance on unseen data and by stability over time, not by how quickly training loss drops. It also means you understand that the optimizer is shaping the path the model takes, not just how fast it moves. The learning rate is the single most important stability control because it determines how big each update step is, and in deep learning, step size interacts with everything else. If the learning rate is too high, training can become unstable, with loss oscillating, exploding, or failing to settle because updates overshoot good regions. If the learning rate is too low, training can crawl, get stuck on plateaus, or appear stable while failing to learn meaningful structure within a reasonable number of updates. Beginners often interpret slow learning as a model architecture problem, when it can simply be a learning rate that is too conservative. Conversely, they may interpret fast early improvement as success, when it could be a sign of an overly aggressive learning rate that will later destabilize. A safe mental model is that learning rate is the steering sensitivity of training, and different phases of training may benefit from different sensitivities. Early training might tolerate larger steps to find a good region, while later training benefits from smaller steps to refine without bouncing. Learning rate schedules exist because a single fixed learning rate is rarely ideal from start to finish. A schedule changes the learning rate over time, often starting higher and then decreasing, so the model explores broadly early and then settles into fine adjustments later. This helps training safety because large steps late in training can destroy a good solution by repeatedly kicking the model out of a stable region. Schedules also help with generalization by encouraging the model to end in a flatter region of the loss landscape, which tends to be less sensitive to small input changes and dataset shifts. Beginners sometimes see schedules as performance hacks, but they are better understood as risk management tools that reduce the chance of unstable late-stage updates. Another scheduling idea is warm-up, where the learning rate starts low and increases gradually at the beginning, which can prevent instability when model parameters are still uncalibrated and gradients can be erratic. Safe training is often about avoiding sudden shocks, and learning rate scheduling is one of the most direct ways to apply that principle. The concept of batch size is tied to both optimizers and learning rates, because it controls how noisy each gradient estimate is. Smaller batches produce noisier gradients, which can help exploration and sometimes improve generalization, but can also make training less stable if the learning rate is too high. Larger batches produce smoother gradients, which can make training more stable and efficient, but can also lead the model towards sharper solutions that may generalize less well, and they can hide issues by making loss curves look clean even when the model is learning brittle patterns. Beginners sometimes assume larger batch size is always better because it feels more precise, but precision is not the same as generalization. In operational contexts, you also face resource constraints, so batch size affects memory and throughput, but the conceptual safety point is that batch size changes the noise profile of learning. A stable training setup aligns batch size and learning rate so that updates are neither wildly noisy nor overly rigid. If you understand that trade-off, you can reason about training behavior instead of guessing. Dropout is one of the most important safety mechanisms for preventing overfitting in deep models, and its intuition is easy to grasp when you think of it as enforced redundancy. During training, dropout randomly removes a fraction of units or connections from the network for each update, which means the network cannot rely on any single pathway being available all the time. This forces the model to spread useful information across multiple parts of the network rather than building a brittle dependency on a few features or a few internal units. The result is often better generalization because the model behaves more like an ensemble of many slightly different networks that share parameters. Beginners sometimes worry that dropout is damaging learning because it makes the network weaker during training, but that temporary weakness is the point because it discourages memorization. In a security-oriented mindset, dropout is like requiring multiple independent signals before you trust a conclusion, rather than allowing one strong but fragile cue to dominate. Safe training uses dropout as a way to reduce reliance on accidental correlations. It is also important to understand what dropout does not do, because misunderstanding its role can lead to false confidence. Dropout is not a cure for poor data, label noise, or leakage, and it cannot make a model fair or unbiased by itself. If the training data contains a shortcut that predicts the label, dropout may still allow the network to learn that shortcut, especially if the shortcut is present in many features or is highly consistent. Dropout also interacts with model capacity, because a tiny model with heavy dropout can underfit, meaning it cannot learn the real structure at all. Beginners sometimes interpret underfitting as a sign that the task is impossible, when it may simply mean the regularization pressure is too strong for the available signal. The safe way to think about dropout is that it nudges the network toward robust representations, but it does not replace careful evaluation and it does not guarantee sensible behavior in new conditions. You still need to watch for stable improvement on unseen data and for failure modes that are consistent with overfitting or shortcut learning. Batch normalization is another widely used training stabilizer, and although it is sometimes presented as a complicated trick, its core purpose is to reduce training instability caused by shifting activation distributions. As the network learns, the outputs of earlier layers change, which changes the input distribution seen by later layers, and that shifting can make training harder because later layers are constantly adapting to a moving target. Batch normalization addresses this by normalizing activations within a batch so that they have more consistent scale and center, and then it learns a simple risk scaling and shifting so the network is not forced into a rigid standardized form. The practical effect is often faster, more stable training, and reduced sensitivity to initialization and learning rate choices. Beginners may think batch normalization is only about making values look neat, but the deeper value is that it improves the flow of gradients and reduces internal instability. In an applied sense, it helps the network learn with fewer sudden swings, which is exactly what training safety is about. Even with batch normalization, you should remember that stability is not the same as correctness, and a smooth training curve can still hide problems. Batch normalization can make optimization easier, but it can also create a false impression that the model is learning meaningful structure when it is actually learning a shortcut that will not survive deployment. It can also interact with batch size, because the statistics used for normalization depend on the batch, and extremely small batches can produce noisy statistics that reduce the intended stabilizing effect. Beginners sometimes respond by making batches larger to fix this, but that introduces other changes to learning dynamics, so it is better to understand the underlying reason rather than chasing a single knob. Another subtle point is that batch normalization changes how you think about feature scaling and initialization, often making training more forgiving, but forgiving does not mean safe by default. Safe training means you treat these mechanisms as stabilizers, not as guarantees, and you still validate behavior under realistic conditions. The model should earn trust through evidence, not through the presence of a popular technique. A safe training mindset also includes understanding how overfitting shows up and why deep models are especially capable of it. Overfitting is not only about a gap between training and validation performance, but also about fragile decision rules that break when inputs shift slightly. Deep models can fit very complex functions, so if your dataset has artifacts that correlate with the label, the model can latch onto them and look excellent until the artifact changes. In security and cloud contexts, those artifacts can be logging formats, environment-specific naming patterns, or operational workflows that change over time. Optimizers and learning rates influence how aggressively the model pursues such patterns, while dropout and batch normalization influence whether the model distributes learning across redundant representations or concentrates it. Safe training practices aim to reduce the chance of brittle learning by controlling capacity and encouraging generalizable representations. That includes holding out appropriate evaluation data and paying attention to error patterns, not just aggregate scores. If you only watch the loss number, you may miss the signs that the model is learning the wrong thing. Another important part of training safely is appreciating that the optimizer is not just a tool to minimize loss, but a shaping force that influences what kind of solution you end up with. Two different optimizers can reach similar training loss while producing models that behave differently on new data because they travel different paths through parameter space and may settle into different regions of the loss landscape. Learning rate choices and schedules further shape this path, and regularization mechanisms like dropout change the effective landscape by injecting noise and preventing reliance on specific pathways. Batch normalization changes how activations behave and often smooths optimization, which can change where training tends to settle. Beginners often look for one best setting, but safe training is more about coherence, meaning your choices should work together and match the data situation. If labels are noisy, You may prefer more conservative learning and stronger regularization so the model does not chase random errors. If data is abundant and stable, you can allow more capacity and focus on efficient optimization while still monitoring generalization. Bringing everything together, training deep models safely means understanding the role each component plays in keeping learning stable, generalizable, and honest. Optimizers such as SGD and ADAM decide how gradients become updates, and their behavior influences both convergence and the kind of solution you reach. Learning rates and schedules are the primary stability controls, shaping how aggressively the model learns in early versus late stages. Dropout reduces overfitting by forcing redundancy and discouraging brittle reliance on narrow pathways, while batch normalization stabilizes training by keeping activation distributions more consistent and improving gradient flow. None of these mechanisms fixes poor data or replaces careful evaluation, but together they form a set of safety rails that make deep learning practical rather than chaotic. The core habit for the CompTIA Data AI certification is being able to explain, in plain language, what each mechanism is protecting you from and why that protection matters. When you can do that, you are not just repeating deep learning vocabulary. You are demonstrating that you understand how to keep powerful models from becoming powerful mistakes.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.